So welcome, everybody. Sure, it's good to have that boot camp. Been a long time since we had got to do this fun. Rob Ehlenstein and I used to do a session with performance and availability updates. Just what's new, what problems have people were dealing with, and what are the current issues that people are with. So that's what I tried to do, thinking about what has come up between last boot camp and things that people might be dealing with. The third thing we'll talk about is fast path. And the reason that I want to talk about this is because I've found so many systems where this is just at the default. It doesn't seem to be something that people look at much. Unfortunately, they tend to overlook this, but it's something that can help you out and also help you avoid difficulties as well. This is the Computer World article that announced OpenVMS version 5 when symmetrical multiprocessing was introduced. You might have known that before that we had asymmetrical multiprocessing, where all of the processing for the operating system happened on the primary CPU, and secondary CPU was just used for user mode code only. But in version 5, you had symmetrical multiprocessing, so all of a sudden, all of the CPUs could do IOs, all the CPUs could do user stuff, as opposed to the asymmetrical that was in place before. What this meant, though, is that while all of the CPUs could issue IOs, all of the interrupts still went to the primary CPU. And very quickly after version 5 was announced, first it was introduced, that primary CPU became a bottleneck for many customers. So they introduced FastPath. Now, there were two things that were featured in terms of at the time the FastPath was implemented. One was that we could direct interrupts to any CPU, not just the primary CPU, so that was good. But they also moved away from the use of spin locks that could also be bottlenecks for the entire system. IO lock 8 and SCS was a spin lock that, for example, was very commonly a bottleneck for the entire system. And by the use of device-specific spin locks, you were able to get around the spin lock being a bottleneck for the entire system, because only one CPU can hold a spin lock at a time. So that was only one CPU's worth of capacity that could be used there. But by default, they didn't really know, I think, how to, and they still don't know how to optimize this in the code itself. So basically, the first device that comes along that gets the interrupts assigned to the first CPU, and the second device to the second CPU. Then when you get to the CPUs, you have more devices. You start over where you started with the first 9 non-primary. Now it goes back to the puts with the eventually from there. And when you have that sort of thing, you'll see a display something like this, where you see sequential range of CPU numbers, so it's spread all over. So each NIC different CPU. When you see a display like this, you know that people probably haven't paid any attention to this area, and they could get some optimization from making this a little less broadly spread. Now, why would we want to do that? It can make your system more efficient and also avoid possibility of bottlenecks. These are the commands to assign specific CPUs to, for the interrupts for particular devices to particular CPUs. Set device /preferred _CPU equals whatever. If you look at the DCL sequence, the DCL syntax, you can actually assign a device to a set of CPUs, but I haven't found any practical use for that feature at the moment. this is the point at which we all think, oh my God, I turned off.
It's funny because I can turn off the watch. I turned off the phone. I can turn
I haven't dealt with the challenge of the watch yet. But basically, we'll take a device and assign its interrupts, interrupt state work to a particular CPU within the system with that sort of command. So here we're assigning the fiber channel HBAs both to the first CPU. We're assigning a PE driver with its cluster function to another CPU, and then a NIC that carries cluster traffic to the same CPU. And then down below, we've got TCP/IP services and a NIC that's used for IP. We're assigning those to the same CPU. So there's an example there. Yes.
Would it not make sense for the GA and FGBO because to split them?
Charles, only if you had so much fiber channel work that you were saturating one of those CPUs.
Okay.
Yeah, that would be the only time you'd probably want to put them on separate CPUs.
Okay.
Okay. Here are the ways, the reasons why we would want to assign this optimally. First of all, placing devices with the same device driver onto the same CPU is advantageous because when an interrupt comes in, it's more likely that the interrupt state routine code is in the on-cache CPU for that particular CPU already. So you don't have to load that from memory. The second case is you want to place devices which have to pass packets back and forth between each other onto the same CPU. If they're on separate CPUs, what you have to do is you have to take out the memory management spin lock, you have to do an interprocessor interrupt, and that's more multiprocessor synchronization time to pass the packet to the driver on the other CPU. So if on the same CPU, you can pass it without having to do that interprocessor interrupt. So those two things are the reason to do fast path optimization. We typically try to minimize saturating the primary CPU because it does, even though we've got fast path to spread interrupt work across multiple CPUs, there are still some functions that the primary CPU, the only one that can handle, like firing off TQE. If you don't fire off TQEs, you don't send out oral packets in a cluster, you'll get clue exit bug checks, this sort of thing. There are bad things that happen when the primary CPU gets overloaded to the point of saturation in interrupt state. So we don't want that to happen. It doesn't mean that the primary CPU can't handle some interrupt state work, you just don't want to saturate it ever, okay? Also, VMS schedules processes starting with the highest numbered CPUs. So if that's where it's going to first stick the user processes, we probably don't want to send the device interrupts to those because then we're interrupting the user work. We can get our own work on the lower numbered CPUs. It's probably a good idea. Now, if any CPU still saturates in interrupt state, then as Andrea was saying, you might have to spread things out a bit and end up with something that might not be optimal theoretically, but it's practical and works because you're not saturating CPU. So don't feel afraid to back off from this if you have to get something that avoids the CPU saturation. So that's the whole goal.
Question. Database. How do you use T4 data to see?
T4 could be one way to do that, right?
Monitors,
monitor modes / CPU equals whatever will be another way. Okay. You're using the same underlying infrastructure to see that. You have to be a little careful because when you're running T4 on monitor, the interval that you're looking at may be a whole minute. Is the CPU saturating? Well, maybe it's saturating for 10 seconds. Get a clue exit bug check. Maybe it's so you can't always determine that it's not saturating just because the average doesn't look good over a minute. But if you're doing monitor mode / interval equals 1 second, at least you're tightening up. I'm seeing what the sample is for that second.
Yep.
Okay. All right, so here's an example of where we're directing things a little more optimally. We've got our fiber channel SAN traffic going into a couple HBAs, however, maybe assign those to the same CPU. Here we've got PE driver, which is talking to some number of NICs, cluster traffic, and those same CPU. Here we have TCP/IP traffic. Device, we assign that to another CPU. And then we leave the other CPUs for just user processes and not try to direct interstate work to those. And they'll be able to do their work more efficiently because they have fewer context switches. Okay, this is a case study. We had an 8-node local area BMS cluster of ES45s, and basically cluster traffic was saturating a CPU and preventing them from getting the amount of workload that they needed to get done. They were scheduling holidays in England. I guess in about January 1st, people in England decide they've got to go someplace. So they all pounded on the system at once. And this system is getting overloaded. They wanted to add more systems to it, but they couldn't because adding more systems would just make it worse. So what do they do about it? Well, the customer said, well, we're seeing a CPU saturate, so let's just spread the interrupts across more CPUs than it already is, and that should help us avoid. It's intuitively obvious. That's what should be the solution. And I was saying, no, our best practices are we're supposed to group the interrupts on, and that of course seems to the customer absolutely the wrong answer. So I said, let's do a test. Or the other thing is, of course, we could have used the default VMS settings and continue to do that and just put up with it. But we proposed a test. Let's try it your way, and then we'll try it my way, and then we'll return it to the original and see what happens. And this was the way we measured that. We just measured the total CPU time in interrupt state. So at the start of the test, we spread it all out the way the customer wanted. Total CPU time in interrupt state got higher, which was worse. Then we did it with the best practices, trying to group things as we've discussed. And the total interrupt state time is much lower to the original until they decided, I mean, we got this results and they decided the obvious way to do it. So that took care of the problem. And they were able to then add another couple of nodes quickly to the cluster to handle more additional workload because they had some lack there.
So just out of curiosity, did that manifest itself with RWSCS states?
Most likely, yes.
Well, the reason I asked is we have a cluster that's exhibiting.
Yeah, RWSCS states often mean that you're waiting for a lock request
Right.
to complete. And that could be because the CPU on a remote node is saturated in interrupt state and unable to complete that lock request very quickly. So that could be one possible cause. But your interconnect can also be very slow. Yeah, high latency, that could also cause that. Another case, we had a 3-node cluster, integrity blades. One system was performing extremely slowly. We looked at interrupt state because that's one of the possible things that can be a bottleneck, but we found that there was only about one CPU's worth of interrupt state being used on the system, and that didn't seem like it'd be a bottleneck across the whole cluster. I mean, across the whole 16 CPUs in the box, you've only got a total of about one CPU's worth of interrupt state being used. So it's probably not bad. Well, of course, you come back. We ran SPL.com. This is a great thing to run when you've got high multiprocessor synchronization time. That's the go-to tool. And we found that CPU 0 was holding the EWG spin lock for 95% of the time. Thought, well, that's very odd, and that's not a good thing for CPU 0, because CPU 0 is also the primary CPU on the system. So we looked at show fast path to see, which CPU is EWG on. Well, it's assigned to CPU 0, the primary CPU. It turned out that each EWG 0 had some sort of a problem, so it was generating a constant stream of interrupts. And so what are you going to do until you get a chance to take the system down and do the repairs or change your virtual connector configuration or whatever it is that you do to fix the problem? Well, we just picked a victim CPU number 4. We directed all the CPUs to CPU 4 instead of the primary CPU, and they were able to then get the work done that they needed to do based on that. So that's another case study where FastPath helped Yes.
I had some that wasn't large blade seals. Customers often have more nicks than they need,
Okay.
and they don't insist many use the exclude configuration statement to remove them from the system. Means that in something like that, if it's not used and generating interrupts, generating a lot of uselessness, move it from the conflict for a sysman.
And then it can never be a problem. Good suggestion, Lawrence. Thank you very much.
Yeah, is that dynamic? Yeah, fast path?
Fast path is dynamic. You can do that on the fly. Yes. And if it doesn't work, change it back. Sure. Yeah. And if you need to shift it over time with load, maybe you've got different workload on different days, at different times of the day, you could do that if you needed to. And then show fast path shows you what it is on the system. Now, when you boot, it all gets reset. So you've got to have procedures in your startup procedures to set it to what you want if you want it to set it to a particular thing. Otherwise, it goes back to the defaults. Good questions. All right, let's look at the interaction between hyperthreads and fastpath. Hyperthreading is available on the Itanium processors, these starting with the Montesino chip generation and clear through the i6, the kits and chips. Hyperthreading is available, but you do have to have VMS version 8.3 or later to take advantage of that. The way hyperthreading works is the core can be shared by multiple threads. Two threads in this case. So without hyperthreading, you'll have some amount of execution occur on a core, and then it'll do memory access, and the core will have to wait for the contents of memory to be delivered to the CPU for that access, and then it can do more execution, and then you get another memory access, and you've got to go off and do that, and so forth. Another thread can start executing. It does a memory access, and it can come back and do some more execution, but there's some latency there to access the memory. And the whole idea is hyperthreading is to try and minimize the amount of time wasted for the memory latency. Even though Itaniums tend, as architectures go, to have huge memory caches, that wasn't enough, so they figured this would be needed to provide competitive performance for Itanium in the marketplace. So that's the total amount of time to execute this work for this code, given the memory latency. Now, if you have hyperthreading, then when this thread of execution has to do memory access, after a brief delay, you can go and execute on the second thread and get some work done. The memory access will complete, but you've been doing some useful work in the meantime. Okay, when this does a memory access on the second thread, you can go back and after a short delay for the hardware to switch over to the other thread, get execution on the other side, and back and forth. Now, the hardware will try and enforce fairness. So after some period of time of a thread executing, it'll switch over to the other thread. But the total CPU time required for this code, when you compare it with the total CPU time without hyperthreading, can be shorter, and that represents some amount of savings. That's the whole idea of hyperthreading. But in practice, we often turn hyperthreading off. A lot of people recommend just because it can be a problem, let's just disable it. We may be able to take advantage of it, though, if we're careful how we do it. If we try and avoid the problems that it can cause. Hyperthreading appears when you do a show CPU, it appears like you have twice as many CPUs. I've actually gone to a customer site where we did show CPU, and they said, yep, it's got 8 CPUs, that's what we ordered. And we said, well, actually, you've got 4 CPUs, you've got hyperthreading enabled on this system. They had to go have a serious talk with their salesperson about why they've been delivered half the number of CPUs that they had ordered. And but it can fool you because it looks like it has twice as many CPUs. Now, each CPU that you have, though, is not really as powerful as another CPU. You've got twice as many CPUs, but now they can be roughly a little less than little more than half as fast than a regular CPU. You could have some potential savings in memory latency, as we looked like. There's a slight overhead to switch between threads. But really, to take advantage of this, you need to have a workload where you've got more computable or current processes than you have cores. or CPUs and VMSs terminology, okay? So it's aimed at applications that are limited by CPU or memory access time. When they first came out with Adenium, they did benchmark reports, huge database simulations and such, and they would come up with typically about a 5 or 10% gain in performance. And if you were at your limits, 5 or 10% could help, but it wasn't impressive. It's not like double like this. But it looks like, and why is this thing changing? That's odd. I'm not moving fast enough apparently for the computer. Is it on automatic timer or something? I didn't tell it to do that, but maybe it's goading me to move on and get through the whole presentation before the time is over. So we'd like to see more than 5 or 10%, but and you may be able to with later generations. We'll talk about that. Okay, so when you get an i2 server, you could get quad core, dual core. The i4 and i6 can do 8 core or 4 core. Depending on how much money you wanted to spend, those are possibilities. A system might have a couple of sockets. One of them might be populated, one of them might be free, it just depends. But within there, if you have hyperthreads enabled, there are going to be pairs of the CPUs as they appear to VMS that are sharing the same core. So in this case, the co-thread CPUs are 0 and 4 here in what looks like a, looks like it's a 4 CPU system, but it's got only really 2 cores, 4 CPUs as far as VMS appears. If you fill the extra socket, you got more. But in any case, you've got these co-thread CPUs sharing a core. You can tell that from show CPU/full because it'll say what the CPU is, and then the co-thread is the CPU that is sharing the same core. It's basically going to be half the number of CPUs in each case added to the CPU number. All right, so that's how you can tell. Often individual CPUs within a system can be a bottleneck for the system as a whole. The primary CPU, as we noted, could be a bottleneck in terms of firing off TQEs and so forth. You might have the dedicated CPU lock manager CPU enabled in a system. That can be a bottleneck. In a cluster, the CPU that handles cluster traffic via PE driver, that can be a bottleneck. TCP/IP traffic, if that CPU is saturated, that could be a bottleneck for that, or the CPU that's handling disk IOs. I don't know where it's getting the timing from or how to enable or disable that, but it's weird that it's advancing the slides automatically. All right, if you want to see if hyperthreads are on, you can do it with the hthreads command in systelertest, or and that'll tell you if they're capable. It'll tell you if they're currently enabled, and they can tell you if they'll be enabled with the next time the system boots, because those are all 3 separate things. And you can also do that at the EFI level if the system is down. To disable it, you can turn them off. You can also turn them off with the CPU config command at the EFI level. All right, now here's another case study. In this case, the customer moved from a GS1280 alpha system to an Integrity server i2. They had 8 CPUs both before and after. Now, of course, hyperthreads were enabled, as it seems to be by default when you get the box from the vendor. And so it looked like it had 16 CPUs, so that would sound like it was even better. But they had performance problems. They had high interrupt state time on CPU 0, the primary CPU, high counts of user buffer unavailable when they looked in LAN CP statistics for the LLA 0, that's the LAN failover device that handled DECnet traffic. There were some devices that never got fast path support added by VMS engineering. DECnet was one of those because everybody was moving to TCP/IP. Memory channel was another, as I recall. Okay. And they thought, well, maybe this has something to do with the co-thread CPU, CPU8. But when they looked at co-thread CPU8, it was mostly idle. So they're saying, well, it's not stealing many cycles. What's going on? But when you think about it a little bit, what does the idle loop on CPU8 do? Well, sometimes it does nothing. It just sits there waiting for work to do in the scheduler loop. But sometimes it'll go on and zero free pages. So CPU8 in this case was apparently going out and zeroing free pages and doing something, stealing CPU cycles from the primary CPU. Now, if it's truly idle, the Itanium processor will give a hint that says, I'm not doing anything, and then the hardware will tend to run the other thread. But if there's work to do for free page on the, get the free page list zeroed, it'll go out and do that. So even though they thought that there was nothing running on CPU8, work was being done that was stealing cycles from primary CPU. And what they did was they just did a stop/CPU on CPU8, and that solved their performance problems. All right. Our visibility with our tools on VMS is limited with regard to hyperthreads. VMS can't tell when the hardware switches back and forth. It just has to make some assumptions. The scheduler does prefer to schedule a process onto a CPU if the co-thread CPU is idle. So there's a preference there in the code. On hardware clock interrupts, if the co-thread CPU is busy, it'll record, for accounting purposes, half a tick of CPU usage, because it says, well, you're really probably only getting about half since the thread is in use, the co-thread is used. So accounting charges only half as much if the co-thread CPU is busy, and monitor and T-force see what appears to be half as much CPU usage on a CPU if the thread on the co-thread CPU is busy. So that can confuse things a little bit. So here's an example with T4 data. Let's say I'm getting close to, I think maybe I'm suffering from interrupt state saturation on CPU 1. All right, well, I look at this and it only goes up to about 66, 68%. 70%, yeah, it's getting close, but it's not saturated, not fully saturated. I'd expect to say 80, 90% would be saturated. But if I look on the co-thread CPU 5, it's busy maybe 50% of the time over here. You can use TLViz to help you add those together. So here's both of them, right? And you can use the stack command over here to stack those. Oh, now I see periods of time where between the two of them, I'm about 95%. That could be symptomatic of interrupt state saturation. That could be a performance problem. Because my co-thread CPU is stealing half of the cycles. Okay, now let's see, I'll unstack them. I'll look at the options, and now I can add a new item to the list. Oops. All right, within the options, I've got an add item to new, add a new item to list. So I can select the source item number. Is add, and add that to my other one. I give it a title, a name for it. Total CPU utilization for shared core 0, CPU 0 and 4, and then I'll press do it. And then I get a new metric within TLViz that is the sum of those two, and I can see whether I'm saturated. Of course, I could do that for each of the 4 CPU co-thread pairs. And it does look like that one of CPU 0 and 5 is the only core that looks like it's saturating in this particular set of T4 data, but I'm double checking to make sure I'm not getting it on another CPU. All right, this is Hein van den Heuvel. He's not here this week, unfortunately, I'm told, but I've learned a lot from him over the years. But he was writing in the comp.os.vms news group a little while back, and he said he did some experiments with hyperthreading. This would have been earlier Itanium times than the latest processors. He said, at the time, I could not detect any performance difference between hyperthreading not having been enabled and having it enabled, but with all co-threads deactivated using stop CPU. So seeing, and then the tests that I think Robin Eulenstein did some tests, and it was about 1% difference. So it's pretty close. As such, I recommend to always boot with hyperthreads enabled. Go back. I didn't tell you to do that. As such, I recommend to always boot with hyperthreads enabled to be able to activate without reboot whenever you feel like it. This is an interesting comment. You got me started thinking. Your mileage will vary, but from my experience, for underloaded systems where you have less than 50% CPU, hyperthreading does not help, but does not hurt either. And he says for overloaded systems where you have greater than 90% CPU, frequent compute queue greater than 5, I find that hyperthreading allows one to stretch the performance envelope some. So he's giving me a temptation to try this. It gives the system a bit of elasticity, if you like. It softens the knee of the performance curve, and you can expect more aggregate throughput with some response time degradation, of course. I started thinking about, well, how could you take advantage of both of these things? Because we had just been using best practices of just turn hyperthreading off, and that kind of eliminates the possibility of getting any benefit from it. All right, so we got an example, 2 quad-core processors with hyperthreading enabled. Let's assign critical functions to specific CPUs. So let's say CPU 0, of course, is the primary CPU in this case. A lock manager, this could be the dedicated CPU lock manager in a standalone system. It might be the CPU that's handling PE driver and cluster communications for cluster-wide locking in a clustered system. And let's put the fiber channel CPUs on CPU 2, and then let's put TCP/IP BG0 and the NICs for TCP/IP on a 4th CPU. All right, so those are our critical CPUs. And let's stop all those of the co-threads for those. Right, stop all the co-thread CPUs for all of those. This could provide us with the best of both worlds, maybe. Of use hyperthreading on the high numbered CPUs where VMS is first going to schedule the user processes anyway, and then trying to avoid saturation on the other CPUs. Now, if you find you didn't have a lot of fiber channel traffic, maybe you could schedule some user processes on its co-thread CPU. If it's near saturation, maybe you stop the co-thread CPU. All right. And John Reagan wrote in this in comp.os.vms also, if any of you folks are going to get i4s, and of course the same would apply to i6s because the Polson and Tukwila core design is the same. It's just that Tukwila is faster by a little bit, basically. So for the i6s, this would the same would apply. If any of you folks are going to get i4s, the hyperthreading in the Polson is supposedly better than prior chips. Programs that might not have benefited from hyperthreading in the past should try it again with an i4 machine. So I started thinking about this, and I thought I'd pass on to you folks. You might, if your CPUs are your bottleneck, this might be something that you could try to get a little bit more performance out of the system. Okay, the next topic we'll talk about, as my system is goading me to move forward, is cluster interconnect performance. PE driver has to provide guarantees that data will get there, so it will send something and look for an acknowledgement back, and if it doesn't get it, it'll retransmit the packet and take care of the problem. So it'll work, but that can cause some performance problems also. It waits for an acknowledgement for a time equal to the retransmit timeout period. So this is something that it calculates based on what it's been observing in the network and tries to figure out how long should it take for me to get an acknowledgement. And if I don't get an acknowledgement within that amount of time, it says it must have been lost. I'm going to send it again proactively to make sure that it gets across to the other side. Now, if it doesn't see the acknowledgement, it'll retransmit the packet. But if that was all it did, I wouldn't even have it in this session. It does more. Basically, it believes that network congestion is the only thing that could cause a packet to be lost. It believes that its own traffic could be the only thing that could be causing this network congestion. So it's very guilty. It believes that it's got to prevent this network congestion, and the only way it can do it is by reducing its volume of traffic sent. And it believes that there exists some low enough rate of traffic going out of it that could solve the network congestion problem. I've had cases where there's nothing that this VMS system can do to fix the network. The network is just broken, and that's just the way it is. But PD driver drastically cuts back the rate at which it sends packets if it sees retransmissions, and it only increases that rate gradually over time, hoping to find some rate at which it doesn't see retransmitted packets. And that can dramatically and drastically and transparently behind the scenes cut your cluster performance. You may not even know this is happening. So when the packet needs to be retransmitted, or it feels that it needs to be retransmitted, it cuts the transmit window size all the way back to 1. And that's the number of packets that we can transmit at a time before waiting for an acknowledgement. So that can be a problem in terms of performance. So you can transmit a single packet at a time. And then we have to wait for that packet to be acknowledged. Now, once that packet has been acknowledged, it can increase the transmit window size.
Thought it was half. on the
It looks
first
like
floor,
half. It looks like
and
half.
then
It looks
the
like
floor
half.
for the second floor.
It looks like half because it cuts it back to 1, but then it grows back up to half so rapidly that you don't see it. And this is especially bad in multi-site clusters with long distances between sites because you're turning something off and it might take, a millisecond, 2 milliseconds, 5, I don't know how long, depending on distance between sites. I've worked with some customers where there's, 9 or 16 milliseconds between sites, something like this, long distance clusters. All right, so it'll calculate what it calls the safe pipe quota value. I call that the slow growth transition point. That's the value 1/2 of what the current transmit window size was when it had to retransmit the packet. So half of that. So it's cutting it back to 1 and let it growing rapidly up to half, and then it grows more slowly from there. So that's why you had the perception that it was half. Okay. So it allows the current transmit window to grow by 1 unit for each successfully acknowledged packet until it reaches that slow growth transition point, which is half of where it was when it got the last retransmission. And that's why you missed it. It was so quick. After that, it allows it to grow for 1 unit of size for each 64 times the current transmit window numbers of packets. So 1/64 of the transmit window size, then it'll grow by 1. So that grows very slowly over time. Sometimes that can be painfully slow to grow, depending on how much traffic you have. So here's a graph of this going on. So here we got a retransmission, cut it to 1, rapidly back up to half by the time that my sampling took place. And then it grows gradually over time as traffic occurs. Here we have another transmission. So it cuts it down to 1, grows back. I got another retransmission over here. So you can see that the more retransmissions we have, here where we have a lot of retransmissions in a row, you can cut it down so low that it's pathetic. And then only grows up gradually afterwards. So that can be very painful for your performance if you've got traffic that you need to transmit. Okay, so worst case is multiple packets, it's cutting it down and can't grow back up. First retransmit cuts back the current transmit window size and the slow growth transition point. And if you haven't had a chance to recover yet, the second and subsequent transmits cut things back even farther. And that can keep the current transmit window size from growing back up to anywhere near the maximum and cuts your performance. And when the current transmit window size is low, if you've got more packets to transmit at a time than that, you're going to get window full events. Window full events are the symptom that this is hurting your cluster performance. So look for windfall events.
Is this devices you would see in SCACP?
Exactly.
But if you have multiple NICs handling this traffic, this cut down in size would only be on the NIC that's experiencing
It's on the virtual,
transmit issues
it's on the virtual circuit,
on the bridges.
right? Any of those, any
So
of
any
those,
of the NICs.
any of the NICs could cause the need to retransmit if they drop, if a packet gets dropped. But it's the virtual circuit that has the current transmit window size. Now, having multiple NICs can help because you can transmit in parallel on all those NICs. So that can help your performance, but the transmit window size is across all of those NICs. Sure. All right, so here's an example where we've got window full rate is in red. When the current transmit window size is high, have relatively low numbers. When we have current window transmit size has been cut low because of retransmissions, then the window is high. But we do also have some periods where we're getting high window full rates, even when we're up. So that tells me that this 32 here for the maximum transmit window size is probably too low for this application, this workload. It's here we got 32 for the maximum, including those. So you may have to raise your maximum transmit window size. The defaults can be very low, especially with emulators. Emulators have what look like slow. Some emulators have what look like slow depth. ABT version emulated one. That PD driver will take a higher maximum transmit window size for the 1 gig adapters compared to what looks like 500s or 600s on the parents. But this 32 may be too low. We may have to use STACP to raise that to what your workload requires. Now, assuming your network can handle that without dropping all the packets, of course. All right. One of the things that I found was very useful was a new sysgen parameter that's, I think it's only gotten documented in the release notes for certain patch kits so far, but it's called PE2. PE is for PE driver. And PE2 says to PE driver, be a little more patient before you decide to proactively retransmit a packet and cut the current transmit window size and all of the negative effects of that. So here we have packets that are going across, and this is the packets that are retransmitted. Here's because it's received. Sometimes, in fact, I'm finding it to be fairly often. Sometimes PE driver isn't accurately judging how long it should take for a packet to be acknowledged, and so it will proactively retransmit, thinking the packet has been lost. But then the packet arrives, and you see that as a duplicate received in STACP statistics. That's your hint that PE driver unnecessarily retransmitted that packet and unnecessarily cut your current transmit window size back. But with PE2 going up, you can tell PE driver, be more patient, and you can eliminate these unnecessary retransmissions. So if you see a one-to-one correspondence between your retransmits and the duplicates received in the opposite direction on the same virtual circuit, then you know that these are packets that were unnecessarily retransmitted by PE driver. Now, sometimes you'll see matches. These are unnecessarily correlation. Here we have a bunch of retransmits, and there's no corresponding duplicates received on the other side. That means those packets went into La La Land, and they never got to the other side. They were actually lost by the network. PE2 can't help in that case. You've got to go tell your network folks, you're actually dropping some of my packets. You're not supposed to do that. And they'll say, huh?
So maybe the timeout should need tuning?
You mean these packets here?
No, to avoid unnecessary.
That's exactly what PE2 is doing.
Automatic.
PE2 is saying, give me another 10 milliseconds of patience before you time out for each unit of PE2. So if you say PE2 equals 1, then you're giving 10 milliseconds more time. In some clusters, you go change PE2 from 0 to 1 and all the unnecessary retransmissions go away. That's wonderful. We have other customer clusters that are long distance clusters, And their networks are such that it may take a value of 45 or 50 to eliminate the unnecessary retransmissions and time limits. It just depends on your, basically, if you take a value of 1 and increment it and look for retransmissions, you get to 5, maybe go to 10, 15, 20, 30, 40. You know, you can increase it over time, and it's dynamic, so
Mhm.
you can experiment until you get a suitable value. Okay. Yeah, we just talked about it. This packets can be retransmitted by PE driver either because they were actually lost or because it was only the packet or its acknowledgement that got delayed coming back, and PE driver said, it looks like it's lost, and I'm gonna retransmit it anyway. And there's the description of PE2, about 10 milliseconds more patience for each unit of PE2. One of the things I worried about when I first started playing with this is, okay, we're telling PE driver to retransmit slower, being less, more reluctant to retransmit. Is that going to hurt performance itself? But what I've found in practice is the negative impact of PE driver cutting back the transmit window and all of that stuff seems to be much more painful than the rare case where a packet actually does get lost and PE driver is twiddling its thumbs waiting around until a longer interval until it finally retransmits it. That seems to be less painful. I did have one customer where the network interconnect was so bad that it was just dropping packets all the time. And in that, there were maybe 2 or 3 customers that I had with that sort of a problem. And in that case, we did a more drastic solution where we went in and modified PE drivers, data structures, and lied to it and told it, no, things are fine. Keep transmitting. Don't cut back. And we're able to give them acceptable performance in that case. But that's more of a sledgehammer approach, and that's pretty rare.
Since
It was a long distance cluster, and the network folks were not cooperative at all. It was just dropping, a large percentage of packets compared with what it should have, and they just had to make the cluster work. So I made a little tool called the FSA, full speed ahead, like told it don't care about the retransmissions, just keep on sending. Go ahead and do the retransmits, but keep on sending and don't cut back the transmit when it sends. All right. All right, so this is the technique. If we see the retransmitted packets show up on the other side as duplicates received, then we know that they were unnecessarily retransmitted, and PE2 can help. If they don't show up as a as a duplicate packet on the other side of the virtual circuit, then it really did need to be retransmitted because it was lost. So we can't help that with VMS. And here are the packets. So we've got a node 3 here, and I'm showing the 4th screen from SCHCP. And here we have transmits. So I had 5 retransmits. If I saw that went from 4 to 5, I knew I had a retransmit occur. Now I can look over the other side. Do I get a picture received? Did that go from 1 to 2 at the same time? Then I know that it was an unnecessarily retransmitted packet. And we've got tools that automate looking at those differences, so you don't have to do all the displays manually. Maximum transmit window size is the size to which PE driver can grow. The defaults for a single 1 gigabit path VMS will pick 32. For 2 gigabit, 1 gigabit paths in parallel, 64. 10 gigabit paths, 64. 2 10 gigabit paths in parallel, 128. This is something that you might consider grading. Emulators like Parris will typically have 16 for the maximum transmit window size for default because they think it's a DE500 or DE600. If you're using ABT-ware and you're emulating a 1 gigabit, you get the 32 for each one instead. And these are the defaults. It doesn't mean the adapter can't handle more because you're really running in an emulator on some fast x86 processor, probably with 10 gig Ethernet hardware. So you can raise this size often without causing retransmissions or packet losses, but the defaults are what comes out of the driver looking at the hardware and determining what it thinks the hardware can do. All right, so if you get window full events often, you might want to consider raising the transmit window size. I did this at one customer's thing. The defaults were like 32, and I found that if I raised it to 128, it did fine, and we got great performance, many fewer window full events. But if I raised it to 256, their network could not handle that without losing packets. So I had to pick a value that was optimal, and it was less than the maximum that, this PD driver will run up to 1024 in theory, but your network might or might not be able to. And that's the command, set VC, specify the node, or it could be asterisk for all, flash window equals, and the direction, the number. Direction could be transmit or receive. The rule is when you raise the window size, you always want to raise the receive side first because it's accommodating the packets, and then raise the transmit side. When you're reducing it, you want to reduce the transmit side first and then reduce the receive side. If not, you're probably going to get PEA 0 excessive packet losses messages on OpCom because you've given it the opportunity to send more packets than it can possibly handle on the other side. Okay. There's my notes about emulators. Let's talk about host-based volume shadowing and mini merge policies, write bitmaps, and reset thresholds. If you know how host-based mini merge works, it's basically fixing up things that have happened after a node crashed, potential differences in shadow set members. That happens after a node crashes. Mini merge is much faster than a full merge, so we want to do that if we can. Updating write bitmaps requires that we send a packet across. At one point, they could actually send these in parallel, but they ran into some undiagnosed problems, and now we are back to sending them sequentially to each of the remote nodes. So the number of write bitmaps you have will determine the number of round trips you've got to make to another node before you can finally do the write to the shadow set. Let's say you have a 6-node cluster. There are 6 write bitmaps by default. If you haven't even looked at this, and you could be sending updates to 5 other nodes before you can actually do the shadow set. If you have a multi-site cluster where there's some latency between the sites, that could be even worse. So you might want to look at your host-based mini merge policies because of that. These write bitmaps get periodically reset. Basically, when the number of blocks that has changed reaches a certain level, then you'll do a reset. That pauses IO to the shadow set. And so there's a brief pause in IO. You don't want to do that too often. And I've seen cases where people still have the original 50,000 block reset threshold on their host-based mini merge policies. Later on, VMS changed the default to 1 million blocks, but many folks still have that. What I like to do is use a rule of thumb that says basically about 5% of the capacity of the disk is probably a reasonable first estimate for reset threshold time. Basically, what this would mean is that if you have to do a mini merge, it's still going to be 20 times as fast as the full merge, because at maximum you have 5% of your disk that has changed and would have to be fixed up. If you set a threshold of 10% capacity, that would still be 10 times faster than a full merge if you wanted to do that. So, but as a rule of thumb, I've set it roughly 5. That seems to be a lot better than the defaults of 50,000 blocks or 1 million blocks. So that's the material that I had for you. Does anybody have any questions or contributions or things that they've run into? Been useful.
Thank you.
All right.
And it's always that damn network group causes problems.
Well,
And they doesn't.
yeah, they'll say the network's working fine.
And isn't that usually the case? Like, I'd say 50% of the time, you say it's a network and that's an accurate presumption.
that the network is the problem?
Yeah.
The fun ones are when it's actually high IPL. Someone just spinning at a high IPL, it
Yeah,
looks
but how
like
is
a
that?
network. It's tougher to tell.
Yeah.
Network group's always doing something, that's, and they don't tell you.
But they deny it. Yeah, thank you.
And they always say, tell the system first, you said, what's wrong with the system? I was gonna do it.
Sounds interesting.
Thank you.